Okay, so now that you've gotten an overview of what the Executor interface looks like, I'm going to show you an example, very simple app that uses the Executor interface in a fairly simple way. And this is our PrimeChecker app. We'll talk about what that app does and how it works. So you can actually download the app here if you want to play around with it. I have a whole bunch of different implementations, and we'll look at all of them later on in the course. So this is the very simple one. And this uses the Java Executor framework to check if n randomly generated numbers are prime. And you get to select how many random numbers will be generated. So let's take a look and see how this works. First, note that this app is what's called embarrassingly parallel. What does it mean to be an embarrassingly parallel app? That means that there's no data dependencies between worker threads. And so as a result, everything can kind of run at the same time. This is also a compute-bound app. And that means that the computations that are running, checking to see whether numbers are prime or not, don't have to block on I/O. So if you recall when we talked about different types of thread pools and how many threads should be in the thread pool, you would typically want to have as many threads in the thread pool as there are cores on your computer. The prime runnable class is a runnable, and it defines a very simple-minded way of checking to see if a number is prime. So here's the method isPrime, and you can see what it does is it just goes through the method, cranking away from sort of 2 to n over 2, and it checks to see if you multiply these factors by each other, do you end up getting a result that will be 0 when you divide the things together. If you end up with nothing being divided, then it's a prime number. And if you find something that matches, then you have the smallest factor. So it returns the smallest factor. So that's a very, very simple-minded way of doing prime checking. And the reason we do this, honestly, at least we do it this way for this example, is just to burn CPU time. We're just trying to have something that'll take a while to run. And there's obviously more efficient ways of computing that, like the sieve of Arathnos or whatever, and other techniques. And I actually have some of those implementations later. This particular implementation, because we're just looking right now at the Executor framework in its simplest form, uses an executor that's implemented with a fixed size thread pool. We get that by saying new fixed thread pool, which creates a pool that will use a fixed number of threads operating off a shared unbounded queue internally. And we make n, where n is the number of, where n is what we're requesting the number of threads in the pool to be, to match the number of processor cores on our computing device. So there's a method called runtime.getRuntime.AvailableProcessors, and it returns the number of processors that are available to the underlying Java execution environment, which, let's say if we're running on a quad-core machine, this would be 4. So as we said before, it's a compute-bound task. Might as well go ahead and have it be set to the right value. And that's why we do this, because isPrime is a compute-bound task. So there's no sense in having, 2n number of threads, because only n of them are going to be able to run at a time anyway. Here's how the actual program works. This is using a little simple Java 8 streams mechanism, which I'll walk through in a second. And this is actually driven by the main activity of the app. So if you look at the app, it's an Android app, and it sets up the GUI, and it has this code nestled in one of the parts of the program, the start computations method, which is part of the activity. Activity is an Androidism that can interact with the user. So what we're going to do here is we're going to make count number of random numbers. So count is just whatever parameter you give. In fact, I should have showed you this before. If you look at the app right here, this is the count. You can put in whatever you want to have there. That's just the count. So there's 25 of them or whatever. And so that's that value. And so we're going to have count randomly generated longs between the range of s max value minus count and s max value. And s max value is the maximum size of a long, which is pretty huge. And so we're just trying to generate random numbers within a range. And the reason that we do it like this is so we'll end up with some duplicates most likely. Then we take this longs method generates a stream of random numbers. It'll have a stream of count random numbers between this range. And then for each of those random numbers, we're going to go ahead and execute the following code. So this is just a Java 8 for each method. And you can see what it's going to do is it's going to say, this is a random number. For each random number in the stream, execute this object. And here's a new prime runnable. We'll talk about what prime runnable is in a second. And what it basically is going to do is it's going to kind of wrap that random number up in something that can do the computation to see whether or not the number's prime. So we'll look at prime runnable in a second. So we make a new prime runnable, and then what happens here is that this runnable will be queued in a queue that's managed by the fixed size thread pool that we created way back here when we said new fixed thread pool with this many threads. So that's going to put stuff into that queue, and then the threads in the pool will pull the things off the queue and run them to completion. Here's what prime runnable looks like. So prime runnable is a runnable, so it implements runnable. It's got a couple of fields we use to keep track of what the original prime number was, and we keep track of the Android activity. We need that Android activity so we can later get some results back and display them to the user. And the constructor, as you can see here, stashes that stuff away. We then have the isPrime method, which I showed you before, which chugs away to see whether or not the parameter that's passed in is prime. And then here's the run hook method. The run hook method is, of course, what's going to get called in that background thread because prime runnable implements runnable. So it's got the run hook method. So this is going to run in the background, and what it's going to do is it's going to ask, is this prime candidate, which is what was passed in here in the constructor, is this prime candidate prime or not? And it'll give back the smallest factor as the result of that. So the hook method invokes isPrime. So any questions about that? I mean, it's really pretty simple, but we're just basically creating a bunch of random numbers. We're turning them into prime runnables, and each of those things will then be run. And when they run, they can check to see whether that number is prime. And then based on what they get as a result, they'll display that to the user. The win of this is even though there could be a lot of prime runnable instances, there could be lots of objects of prime runnable, they will be run on a much smaller number of threads, namely the number of cores on the machine. So we might have 1,000 prime runnables, but there'll only be, say, 4 threads in the pool, and everything else will just be queued up in this queue waiting for their chance to get an opportunity to be run. And we can control these things programmatically. All right, so that's just a quick summary. If you want to see the full-blown glory of the app, you can download it at that link and play around with it and run it. So let's talk about the pros and cons of this approach. So the Java Executor interface is nice because it enables the number of threads in the pool, and the type of these threads to be tuned transparently independent of the application logic. So we could come along, we could have a fixed size pool of threads, which is what we did here. We could have a variable size pool of threads. We could have work stealing threads. You could have lots of different kinds of threads. And this logic here doesn't care what the thread pool mechanisms are. And we could even change properties of the threads if we wanted to. We could put thread factories to create them with special priorities or other things, make them daemons or whatnot. So that's the good news. And that's really the benefit of the Executor framework. You decouple how you do the threading from what it is you want to be done in a concurrent way by multiple threads. However, there are some restrictions with this approach, and you should not be surprised about this because it's a very simple interface after all. In particular, the one-way semantics of runnables tightly couple the prime runnable class, this guy, with the main activity. So notice how we have a main activity inside of our prime runnable class. So there's a tight coupling between these things. And this tight coupling gets us into trouble in various ways, not the least of which is anytime we do a rotation of the screen in Android, go from portrait mode to landscape mode or vice versa, that will destroy the existing activity, and so we'll end up not being able to continue the computations running in the background because these things are tightly coupled with a particular activity. So that's undesirable. Another problem is that the isPrime method is also tightly coupled with PrimeRunnable. So as you can see here, we have a specific implementation of isPrime, this one, that is the very inefficient one, and that is hard-coded with the PrimeRunnable class. So if we want to change how the computations occur, we're going to have to go in and modify this particular piece of code. And our program is also strongly dependent on that. So lots of rework would have to be done if we made any changes. Yet another problem is the lack of lifecycle operations on the Java Executor interface itself. So there's no way to be able to control its lifecycle. All you can do is execute something. You can't shut down the executor. You can't find out how many tasks are running in it, and so on and so forth. So a couple problems. You can't interrupt or cancel running tasks. They can't be shut down. You can't handle runtime configuration changes gracefully. You have to start over again from the beginning, which is not the way you want your Android apps to work. So this approach, while it does give us some concurrency, has lots and lots of limitations. So it's very simple, but it's also kind of lame.